Public conversation often frames artificial intelligence as a universal solution for any data problem, from creative writing to enterprise-level logistics. For organizations predicting complex time series data, the industry standard is a deep learning architecture known as long short-term memory, or LSTM. It is a neural network designed to identify patterns across long sequences of historical information. However, these models require immense volumes of data and significant processing power, leading to high computational costs that many businesses overlook. This creates a fundamental tension. Does the increased accuracy of a deep learning model justify its massive operational expense? To find the answer, analysts use a performance measurement methodology called forecast value added, or FVA. This compares a complex algorithm's trajectory against a zero-cost baseline. FVA calculates the exact accuracy gained beyond a basic moving average. If this tiny improvement fails to offset data processing costs, the FVA becomes negative. FVA provides a mathematical proof that algorithmic complexity is only an asset if it generates a measurable return on the investment. There are environments where deep learning is the correct choice. Pharmaceutical drug sales are defined by erratic patterns and high volatility that challenge traditional forecasting. In head-to-head pharmaceutical tests, LSTM models significantly reduced error rates compared to popular industry benchmarks like Facebook's Profit model. LSTM succeeds here by automatically identifying nonlinear temporal features, complex relationships in the data that standard models often fail to see. In these volatile scenarios, the accuracy gains provided by deep learning models justify the increased computational resources they consume. But consider a market widely associated with extreme volatility and advanced automation, cryptocurrency trading. Comparative research on Bitcoin price forecasting found that traditional statistical models, like ARIMA, actually produced lower error rates than the more advanced LSTM. This happened because these financial datasets contain strong linear components. Simple statistical methods excel at capturing these study trends, while complex models can sometimes overanalyze the noise. We see the same pattern in mechanical engineering, specifically when predicting the performance of cryogenic thermodynamic systems. When predicting thermodynamic output, the tree-based random forest model, a more traditional machine learning approach, consistently outperformed the deep learning capabilities of LSTM. The random forest model achieved higher accuracy while requiring a fraction of the computational power, all while remaining more interpretable to the engineers using it. The data suggests that over-engineering a solution can create a financial liability, as the most complex model is not always the most effective one. This presents a choice for data scientists. If deep learning masters chaos and traditional models master linear trends, which architecture should define a business strategy? The highest recorded forecast value added usually comes from hybrid architectures that use multiple algorithms simultaneously. Researchers have already demonstrated this by combining ARIMA with LSTM to predict groundwater levels, leveraging both linear and nonlinear logic. A similar approach is used in retail, blending the efficiency of models like light GBM with the pattern recognition of LSTM to optimize supply chain sales forecasts. Modern forecasting gains are driven by the integration of these distinct mathematical approaches. In a hybrid system, the labor is divided. A traditional algorithm serves as the foundation, mapping out the clean, linear trends. The deep learning model is then applied to the residuals, the volatile, non-linear patterns that the basic model cannot see. This coordinated approach uses FVA to ensure that every layer of complexity adds a measurable advantage, resulting in a forecast that is both computationally efficient and highly accurate.